Hi, I am Costantino and I thank you for listening to my talk, and I thank the organization for giving me this nice opportunity. The talk will be based on a preprint that we released on the archive on last July, and it is a work that was carried on with collaborators Andrea Maselli, Paolo Pani and Massimo Vaglio at the Sapienza University of Rome. The idea of the work is to explore the ability of future gravitational wave detectors such as LISA and the Einstein Telescope to measure fundamental scalar field interactions. And we will do so by exploiting the connection between boson stars and scalar fields. Briefly, what is a boson star? It can be defined as a self-gravitating configuration of a massive complex scalar field. Now, these configurations can be arranged in such a way that they are both compact and massive, and these conditions are realized in the so-called massive boson stars models, which are characterized by a quartic self-interaction such that one is in the strong coupling regime. So in this situation, you have compact and massive boson stars, therefore they can act as potential sources of gravitational waves. Boson stars have distinctive properties, and for example, they cannot have arbitrarily large masses. They have a smaller compactness when compared to neutron stars and black holes. They have a non-zero tidal deformability, and they have a spin-induced quadrupole moment which differs from that of a black hole, and we will parameterize this difference with this auxiliary function kappa. Of course, they will also differ in higher multiple moments, but we will neglect these effects and we will just concentrate on the quadrupole moment. Now, what is remarkable is that all these properties can be parameterized by a single effective coupling, which we will call MB, and it is just a simple combination of the original couplings of the Lagrangian. So this MB will be our main focus. Let me anticipate what it will be the main result to motivate the rest of the talk. So the main result will be that both the Einstein Telescope and LISA have the potential to measure MB with very good accuracy. So let's see how MB enters in the boson star properties. First of all, MB sets the global mass scale. So let's see how. In this plot, you see that the maximum mass of a boson star is proportional to MB, and the proportionality constant in the limit of small spins is equal to 0.06. So, from these orders of magnitude, you also see that you can set up MB in such a way that boson stars will have stellar masses, or in such a way that they will be supermassive. Of course, these two scenarios, they will correspond to two different realizations of the theory. It is not the same realization of the theory. It's two different branches. Now, the same quantity, or more precisely, the ratio of the mass of the boson star and MB, it determines the value of the tidal deformability, which you can see in this plot. It can be quite high. And finally, the very same ratio also determines the value of kappa, which enters the expression of the quadrupole moment. Now, the first thing to notice is that the range of values spanned by kappa are 1 or 2 orders of magnitude higher than the value of kappa for black holes in general relativity. So this helps to discriminate between boson stars and black holes. The second thing to notice is that since both kappa and lambda depend on the same ratio m over mb, there should be a relation among these two quantities. So, actually we were inspired by what happens in neutron stars, in which you have the so-called log-Q relations. These relations are very simple relations which connect quadrupole moments and log numbers or tidal deformability, and we see that even in this case for boson stars there is such a simple relation. So if you plot the value of kappa against the corresponding values of lambda in log scale, you find that the relation is basically linear. So I want you to notice that while it is true that there should have been a relation, it is by no means obvious that a relation should have been so simple. So this is a very nice result, and I will come to this result at the end of the talk. Let me just stress, however, that this is a result which, similarly to what happens in neutron stars, it holds in the limit of small spins. Now, we have all the ingredients to talk about parameter estimation. So, parameter estimation of what? What is the scenario that we imagined? So, we assumed that our detectors will detect waveforms originally emitted from binary boson stars. So the system that we study is a binary boson star system. First, we have to model the corresponding waveform, and we will focus on the inspiraling part of the waveform, and we will model it as a post-Newtonian expansion in the frequency domain. So the expansion can be split in an amplitude part and in a phase part. So since most of the relevant physics is encoded in the phase, we basically truncated the amplitude to the leading order in the Pn expansion. While the expansion of the phase is a little bit more involved, in the sense that there will be a 0th order piece, which is the same that you would use for binary black holes, which is then corrected with two kinds of corrections. One class of corrections comes from quadrupole corrections, so from the fact that the quadrupole moment of boson stars is different from that of black holes, while the second source of corrections comes from the fact that there is a tidal deformability when we consider boson stars. So when we sum up all these pieces, we obtain our post-Newtonian waveform for boson stars. Once we have a waveform, we can forecast the uncertainty with which we can measure parameters using a simple Fisher matrix formalism. And in this formalism, basically I want you to notice that we will not estimate parameters such as the quadrupole moments or the tidal deformability, but we will estimate directly the couplings of the Lagrangian, or actually we will estimate directly MB. So this is a direct measurement of the couplings of the Lagrangian. Now, these are the configurations that we considered. So we set the mass scale in such a way that for the Einstein Telescope we will detect boson stars of stellar mass. while in the case of LISA, we will detect supermassive boson stars. We set the individual masses in such a way that the heavier mass is equal approximately to 0.06 times mb, while the ratio of m over mb for the lighter mass will be equal to 0.05. What about the spins? We considered three classes of spin pairs. We considered a pair of small spins, a pair of moderate spins, and a pair of high spins. And finally, we set the luminosity distance to 500 megaparsec for ET and to 1 gigaparsec for LISA. What about the final results? So, the results can be expressed in these two plots. The quantity which is plotted is the relative uncertainty of MB in percentage. And you see that for both the Einstein Telescope on the left and for LISA on the right, for all the configurations that we considered, these uncertainties are below 100%, which means that we can obtain a meaningful measurement of MB, although in some cases this measurement is only marginally meaningful. However, in many other cases, the measurement is not only meaningful, but it's also very good, because the relative uncertainty is of the order of the percent or even smaller. So, since I don't want to run out of time, let me stress what is the relevance of these results and in which directions these results can be improved. First of all, the Fisher matrix formalism is only an exploratory tool. So it is known to give only order of magnitudes estimates, and well, it is not fully rigorous. However, it gives encouraging prospects in our case. So it sets the case for repeating the analysis by means of a consistent Bayesian framework. So there is also another direction which in our opinion it is worth to be explored, and it is the following. We found a relation between kappa and lambda which is very similar to the love-Q relations that exist for boson stars. Now, this of course induces a natural question, which is the following. Is it the case that there are love-Q relations also for boson stars? And we cannot answer this question right now, because basically we only analyzed one single class of boson stars, namely the ones with quartic self-interactions. So in order to answer this question, so in order to understand if there are universal relations for boson stars, we should also explore other kind of couplings. And so we believe that it is worth to be understood if it is the case that universal relations can be expanded also to include boson stars. Okay, so since you are here, it means that you didn't lose your patience during this talk, during this video. So I have to thank you again, and of course, if you have questions, if you have discussions, if you read the paper and you have questions or discussions about the paper, you are welcome. And so thank you again, and thanks again to the organization, and enjoy the rest of the symposium. Thank you. Bye.